Good morning, good afternoon, good evening, folks. Thanks for joining us this fine Wednesday morning here in the U.S. In Cleveland. Jim Vajda joining us from Cincinnati. He's actually on vacation today, so thanks for making the time for us, Jim.
Always got time for these and our audience at Seven Signal.
We certainly love our audience joining us each and every Wednesday for these topics. So we'll go ahead and get started here. I've got a couple of housekeeping notes. For those of you who are new to these webinars, just a few things to talk through. Our YouTube channel has all of our archived webinars. So if you're looking for an old topic or if you miss one, you'll receive an email from us about an hour and a half or so after the webinar takes place with a link to the recording, so you can certainly share that with your colleagues. For those of you who are joining us for CWNP, continuing education credits, we can share those with you as well. These webinar topics are certified by CWNP. Please use your business email address when you're contacting us. We've got some pretty strong spam email filters through our AppRiver account, and I may miss your emails as they come through. I know Forrest is giggling right now, probably in the background, because I missed a handful of his emails requesting some CE credits and certs along the way here, so I apologize for that. But please use your business accounts moving forward. You can get access to our IDC ROI report by going to wirelessmonitoringroi.com, and I'll drop that into chat. If you haven't already done that, it's definitely well worth the 5 minutes or so that it'll take to put your information in there and show you the value of Seven Signal and what we bring to your organizations. We won't do a product tour today. We stay away from those on our Wednesday webinars, but you can go to a live product tour at go.sevensignal.com/tour, and we can walk you through all of our products. No spin, certainly a no spin zone there. Or if you prefer to listen to our webinars via podcast, you can search for the Digital Experience podcast from Seven Signal, or just Seven Signal, in whatever medium you're using to listen to your favorite podcasts. Also today, I want to welcome to the 7 CWE Club a handful of new certified wireless engineers. 2 from Seven Signal, Laurent and Jeff. We've got Chris from RF Works, Michael from the George Washington University, we've got Cord from EBSCO. We've got George from Cognizant, Gustavo and Ilyu from Nike, and Matthew from Tetra Tech. So thank you very much for those for joining those certification tracks, and congratulations on completing those. Well, Jim, we've got a handful of trivia questions today, and they're kind of various levels of difficulty. As always, we do send swag out to the first person who answers these correctly. We do dive into the database here and find out who was the first to answer these correctly. Anyway, we've got 3 questions today. The first, I'm going to launch this up, is around MCS, since that is one of our topics today. But it says MCS Index describes the modulation type and coding rate used across a set of these. There is one correct answer in this poll. So let's see how we all do. And as I see these answers coming through, it seems like this is going to be an easy one for folks.
Yeah, I hope so. Good one to set the table for what we're going to talk about today, too.
Indeed. Let's share those results. Jim, how did the audience do?
Excellent. 76% got the right answer. It's all of the above.
Right on. Well done, folks. And let's see. Let me hide these results and get the next one up here. Another kind of beginner one, I'd say. So let's launch this one, see how everybody does. Another chance to win some swag here. It says, what metrics does mean opinion score, MOS, take into account? Listening quality, transmission quality, conversational quality, none of these, or all of these? Folks are rapidly putting their responses in. Just over 50% of you have voted so far. Let's close this poll out and share the results. Jim,
A
how
little
did we
bit
do on this
trickier
one?
here. Well, I think people are normally thinking packet loss, latency, and jitter, but the way the algorithms work, they sort of funnel them up into these quality numbers as part of their calculation. So in this case, it's all of the above, isn't it, Mr. Cook?
Indeed it is. Indeed it is. 38% of you. So we've got some training to do there. So you guys are in the right place because we're going to talk through that today. And now this one is a dandy. So we'll see how you do. This one we had to do a little research on. Is that right, Jim, when we pulled this one out?
That's right. We had to go to the reference material
The reference
to
material.
find us a more difficult question.
All right. According to the G711 codec, what is the threshold below what many users are unsatisfied with the call quality? Is it 2.6, 3.6, 4.0, or 3.1? Let's close this poll out and see how everybody did here.
Well, this is a tough one because it's specific to the codec here, G.711, and the correct answer is 3.6.
All right, 20% count there, got it correct. Again, you guys are in the right place. You're going to learn a lot about that today. So let me hide that poll and welcome you all again. We've got a great topic ahead of you all today, MCS, MOS, and the digital experience of end users. And with us today, as you can see in the video here, is Jim Vajda, resident CWNE, and our Chief Wireless Officer. So Jim, I'm going to get you the controls here, and we'll start sharing your screen. Again, and I'm locked up. I don't know if you can take the controls here, Jim.
Sure. Yep.
Sorry about that.
I'll make myself presenter.
Great.
And off we go.
And I've got your screen.
Excellent. Right. So quick about me slide. I'm Jim Vajda, Chief Wireless Officer here at 7Signal, wireless network engineer for 10 years or so, and links to Twitter and my socials and my my blog and my amateur radio call sign is all right there. But today, kind of giving an update on Mobileye and what we're doing at 7Signal in terms of recent releases and our strategic vision going forward. So a couple of the important themes that we're incorporating are a focus into the digital experience of end users. And in that we mean we're looking very carefully and with a sharp focus on Wi-Fi performance. But we also want to put that in the context of the overall performance of end-to-end networking and application performance, and be able to tell you, if that end user had a good or bad Wi-Fi experience, but also if their complete digital experience was good or bad, and relate that to what we know about Wi-Fi, where our core competency is, and also to other aspects of networking as well. So we'll talk more about that. On the back end, in the last 6 months or so, we've really upgraded our cloud architecture. There's not so much to see in the UI, but we're ready to scale because we've gone from organizations with hundreds of users deployed to thousands of users deployed, and now we have customers we need to support with tens of thousands of agents deployed. So supporting that level of scale, we've started to get ready for. And then our architecture in general is becoming more flexible, and you'll see more and more of that in the future here. But I want to focus today on digital experience monitoring. So Gartner says that DEM technologies monitor the availability, performance, and quality of experience an end user or digital agent receives as they interact with an application and the supporting infrastructure. So really, it's trying to boil down, that nurse with a tablet, is she having a good experience interacting with the applications that IT is delivering? Doesn't matter if they're cloud applications, doesn't matter if they're, locally hosted. What's the experience going to be like, and can we predict if it's good or bad, and if there's some interventions we need to take? So our focus for the key performance indicators of digital experience monitoring, especially in the Wi-Fi part of things, we're going to focus on two metrics. To look at Wi-Fi, we're going to focus on MCS, which we'll define and talk about why that's important. And to look at end-to-end performance, we'll look at MOS, and we'll talk about that and talk about some of the new things there as well. And actually, we'll start with MOS. So, the reason we're looking at MOS is so many enterprise applications, just like this webinar, are very sensitive to latency and packet loss, just like traditional VoIP applications are. So you can think of all the collaboration tools we're using now, particularly, and those the importance of those has really grown as the workforce has become more remote. But also VDI solutions, Citrix and VMware Horizon come to mind. And network throughput limitations are still there, but it's not like the old days when you really had severe bandwidth limitations on the network. And where we do have bottlenecks in most enterprise networks, they tend to be at the edge on the Wi-Fi. And by measuring the digital experience with 7MCS, which we'll talk about as we go, and MOS, will capture that, even if we're not laser focused on looking at throughput. So there's been a real evolution from using MOS just to measure call quality in traditional VoIP environments to using MOS to really get a better understanding of if the network is prepared and delivering the performance required for the modern applications we're using in the enterprise. So MOS, for the uninitiated, it is an acronym for Mean Opinion Score. It comes from quality studies of VoIP calls, where people on calls were sort of rated the quality the quality of the call on a scale of 1 to 5, and then those ratings were correlated with sort of the hard numbers we get from the network around packet loss, latency, and jitter. So when you only have those numbers, you can then predict, using a MOS algorithm, the quality of the call. So that's MOS, and very simple scale, 1 to 5, 5 being excellent, 4 being good. When you get into the 3s, that's where you should start, being a little bit concerned. But we're really happy to announce that we now are doing MOS testing on Windows. So before we supported Mac OS for a MOS test, and Linux as well. And with our most recent Mobileye release, which is coming soon this week, you'll see MOS testing rolled out for Windows. We'll be able to give you that insight onto your Windows fleet as well. So next, let's talk about MCS. So The MCS index is really a simplification. So you can think of it as taking a whole boatload of data rates that are possible in Wi-Fi and just rating them on a scale of 0 to 11. And 0 is poor, 11 is the best possible data rate imaginable. And that's one way to think of MCS. Really, what it's doing is taking, like you saw in the trivia question, all these, this combination of guard interval and channel width, and so on, and just breaking it down by the modulation and coding scheme used in each one. So again, it simplifies things. One thing you'll notice in this MCS table, and you can see the whole table at mcsindex.com, really good reference there, is that for HT, VHT, and HE, which are 802.11n, 802.11ac, and 802.11ax, they don't all go as high. But for the most part, if you're at 64 QAM, you're going to probably be having a good Wi-Fi experience. So we'll talk more about that. But the MCS index is really valuable because the full table of data rates is just massive. So it's hard to look at a data rate and think, well, is this a high quality connection or not? Because depending again on the channel width and the generation of Wi-Fi, or sometimes we'll call it the PHY in use, that data rate may not reflect the quality of the RF and the channel conditions involved. But the MCS index always shows that. So, why did we land on MCS? It seems like we should use signal strength or something simpler for measuring Wi-Fi performance. And one of the things you learn when you get into Wi-Fi is that a lot of these very simple numbers have a lot of complexity behind them, and can kind of be rabbit holes. SNR is ultimately what's required to support a high MCS, a lot of signal and low noise, and also low interference. But it's actually really hard for Wi-Fi stations to measure SNR. Our signal strength, our RSSI measurement, is pretty questionable. And you can see some examples of that at rssicompared.com, where you can see two or more identical make and model phones or laptops or what have you, measuring RSSI quite differently right next to each other. And unfortunately, the noise measurements that Wi-Fi stations make are even poorer and really are unreliable. So I would advise you to not read too much into those. And so we can't really trust the SNR measurement we get from clients. And data rates, like we saw before, there's hundreds of them, and there's dependencies on spatial streams and the PHY supported and the channel width and so on and so forth that you can't kind of tease out from just looking at the data rate itself. But we like MCS because it really reflects the real performance the station can achieve independently of those capabilities and the channel width and so on and so forth. So, regardless of what the station says its signal strength is and says the noise floor is, MCS tells the truth about what it's doing when it's rate shifting and how high it can go, but based on what channel conditions support. So there's two things in MCS. So there's the coding rate, which we'll start with, and then we'll talk about modulation. So the coding rate is quite simple, and you can see the coding column there in this table, and it's just the number of bits required to send some other number of bits. So 3/4 means it requires 4 bits to be transmitted for every 3 data bits, and that extra bit is used for error correction. So on the lower end of the MCS index, our coding rate is 1/2. But on the upper ends, it gets up to 5/6. We're using fewer and fewer bits for error correction to support higher and higher data rates. So very simple concept there. Modulation, I'm not going to go super deep into, but I will recommend an excellent video from Keith Parsons on YouTube. There's different types of 802.11 modulation schemes, and I'll put that link in the chat actually here. But what we're doing is actually changing a carrier wave. So you can see on the right that the waveform of an RF wave, and we change it, we modulate it, and we just change 2 things with the QAM modulation that modern Wi-Fi uses: the amplitude of that signal and the phase of the signal. So amplitude is easy to understand, is how loud or quiet it is. The phase, you can think of as sort of, are we starting the wave at 0 and going up and down, or are we sort of starting somewhere in the middle? And you can see the phase being modulated on that bottom wave, where at some point it starts at different places than you'd expect. And we modulate those things at the same time. Important kind of takeaways from that is that, the lower the data rate or MCS rate, that has greater differences between symbols. A symbol is just one waveform. And that means that even though the data rate's very low and we can't get a lot of bits through, it's also very robust. The differences are very big between the symbols. So a low data rate can punch through a noisy environment better than a high data rate. And high data rates, smaller differences between symbols, and then a little bit less protection from errors. So that's the trade-off. If we want to go as fast as possible, then our modulation starts to get a little bit more fragile. And just to kind of visualize that, with QAM modulation, you can visualize it on a graph, right, where we're showing phase and amplitude graphed and describing how many different values in the different modulation schemes that Wi-Fi has are available. So QPSK, only 4 values we can represent there, but they're very far apart, right? There's a huge amount of error we can accept in one of these values and still know what it is. 16 QAM, things start to get a little tighter. 64 QAM, even tighter. That's from 802.11n. Then 802.11ac introduced 256 QAM, and the differences between phase and amplitude there are much smaller. And now in 802.11ax we have 1024 QAM, which really takes this to the next level. And it's, when you sort of learn how all this works, it's kind of incredible that 1024 QAM works at all in an unlicensed spectrum. But it does. So when we're looking at the MCS index and looking at our coding rates and modulation schemes, one of the questions is, well, where do we decide what a good connection is, what a good MCS rate is, and what a poor MCS rate is? And like we saw before, really the big changes as we go up and down the MCS index are when the modulation changes. So the coding rate changes here and there. Certainly, getting more aggressive the higher we go. But the big difference is when we change modulation, when we go from, if we drop from 256 QAM to 64 QAM, that's because the channel conditions don't support the precision that 256 QAM requires. And same when we drop down to 16 QAM. Again, that's because we're, too many errors trying to resolve this 64 QAM symbols, and actually we need to use a more robust data rate because channel conditions are not very good. So, how we look at the MCS index is to say, if you're at 64 QAM and above, things are pretty good. Sure, it's 802.11n, but most of us are still using 802.11n when we're in 2.4 gigahertz. And if you've got a clean channel, that should work just fine. It's when we drop from 64 QAM to 16 QAM that, that probably indicates that channel conditions are not great. And if we drop out of that into QPSK and BPSK, that's when we know, look, this transmitter is using a really, really robust data rate because it's trying its best to punch through some noise and interference because it's really struggling to be received on the other end. MCS shifting is a normal part of healthy Wi-Fi. You can think of, a client roaming from AP to AP. As it's getting further from one AP, it's gonna shift down in data rate. But what we don't want it to do is shift down too far before it connects to the next AP. We want to stay up on this higher end so that we can support all the modern applications that we need to and the performance requirements that they have without degrading so far that we can't meet those application requirements anymore. And like I mentioned before, it's really these steps in modulation that reflect the biggest, most significant changes in connection quality. Okay, so that's MCS. One of the things that's always been a challenge in the Windows world is that the Windows operating system doesn't expose the current MCS value to the end user, even though it'd be really valuable to know. So what we did at 7Signal was developed a solution that we're calling 7MCS. So what we've done is taken all those building blocks of MCS that we do get from Windows and turn that into a real MCS value. So you'll see in our release this week that now there's a 7MCS value for Windows, and this is something we're really going to rely on heavily going forward as we're changing the way we're judging the quality of wireless connections. Additionally, a benefit of 7MCS is that we actually standardize MCS. So one of the things you may be aware of is that the way MCS is determined between 802.11n and then 802.11ac going forward is that 802.11n had MCS values specific to every spatial stream combination. So where 802.11n jumped to MCS value 8, that was just a reflection of having two spatial streams. And the other PHYs don't have spatial stream dependent MCS values. So 7MCS takes those 802.11n values and converts them into the standard the other PHYs use as well. So everything is kind of standardized across the board, across Wi-Fi generations. The only difference you'll see is that 802.11n can only go up to 7, 802.11ac only goes up to 9, and now 802.11ax can go up to 11. Okay, so if you're familiar with this problem about MCS on Windows, you're probably wondering, there are these instances where using everything except guard interval, which is what we get from Windows, doesn't tell us what the MCS value is. And so there are some of those instances. Here's one of them, where we have a data rate of 780 megabits per second in an 80 megahertz channel. And since we don't know the guard interval, but we do know the spatial streams, we know that that's either MCS, the true underlying MCS is either 8 or 9. Okay, so we don't know exactly what it is, but we're pretty close. So let's just call that an 8.5. So if you ever see a 0.5 in a 7 MCS value, that's just because there's a little ambiguity. We're not sure if it's 8 in this case or 9, but it's one of those values. And truth be told, when we're evaluating the performance of a wireless client, we don't really care if it's 8 or 9. That's a fantastic MCS value, and it's 256 QAM, right? That's a really high modulation scheme. So in terms of comparing performance, it's still valuable to know. There's a couple other instances, like between 6 and 7. In some cases, data rates are identical. But again, 6 and 7 are both 64 QAM. So we're probably evaluating those the same way we would, we're evaluating them equivalently, is what I should say. So that's really exciting. 7 MCS, you'll see, move further and further forward going forward, and we're really excited to have a solution for MCS for Windows there. You'll also see MOS testing becoming more prominent with what we do in terms of analyzing the end-to-end performance quality that the network can provide. And we're also doing that on Windows now, so very excited about that. And a smaller addition that's worth mentioning in Mobileye in this release is that we're doing automatic recognition of missed AP names. So the clients will pick up the name of your AP as long as it's being advertised in the beacon and probe frames from that access point. So all that, all of that boils into a better understanding of the digital experience of Wi-Fi users, and you'll see us really honing in on that and working towards new analyses around digital experience monitoring going forward. All right, Don, I think we can, if we have some time, take some questions.